Hi everyone, welcome back. So this is part 3 or video 3 of module for beam deflection. So a while ago we discussed about the double integration method. So this is the double integration method. So on this video, we're going to discuss about moment area method. Okay. So for moment area method, it is useful in determining the slope or deflection of a beam at a specified location. So we cannot derive an equation here. Rather, if we are given or we are pinpointed on a certain location, then it's easy to determine the angle of deflection or the slope or the angle of deflection in the deflection itself. Okay. So it is a semi-graphical method in which the integration of the bending moment is carried out directly using geometric properties of the area under the bending moment diagram. As in the methods of double integration, we assume that the deformation is within elastic range. If it is not elastic anymore, then we use a different method, resulting in small slopes and small displacements. Okay, so moment area theorems. So the first moment area theorem. So you have here your elastic curve, you have here your theta A, and you have your theta B. Your theta A and theta B is with respect to your rho because it is changing. Take note that theta A is not equivalent to theta B because your elastic curve here is non-linear. Okay, and since this is your elastic curve at the graph below, it is the moment area method, the moment diagram rather. If you can recall from your integral calculus, we were taught, or you were taught, on how to solve for the area using area of a curve using the strips. Okay, so for this one, we will be using this vertical strip having a dx, thickness of dx, and it will be integrated from point A to point B. Okay, so from the figure, two cross sections of the beam NPQ, separated by the distance dx, rotate through the angle d theta relative to each other because the cross sections are assumed to remain perpendicular to the axis of the beam. Okay, I repeat, the cross section are assumed to remain perpendicular to the axis of the beam. D theta is also the difference in slope of the elastic curve between P and Q. So P and Q, that is d theta. It is the difference in angle. Okay? So from the geometry in the figure, we see that dx is equivalent to rho d theta, where r is the radius of the curvature of the elastic curve of the deformed element. Therefore, d theta is equivalent to dx over rho, upon which, using the moment curvature relationship, 1 over rho is equivalent to m over ei. D theta therefore is equivalent to m over ei dx. So the integral of d theta is equivalent to the integral of m over ei dx from a to b. Okay? So the left side of the equation is theta b, and the left hand side of the equation is theta b minus theta a, which is the change in the slope, okay, between a and b. The right hand side represents the area under MEI. So ito yung area. This is the area. This is the area rather, and this is the change in slope from A to B. Okay. So if we introduce the notation theta b with respect to A is equivalent to b minus theta b minus theta A, the expression can be expressed in the form of theta b with respect to A is equivalent to area of MEI diagram evaluated from A to B. So this is the first moment area theorem. So this is our first equation. Okay? Next is the second moment area theorem. For the second moment area theorem, so you have here your elastic curve still, you have there your point P, Q, A, and B. So this time, we are interested in the displacement between point A and point B, and we refer that as the tangential displacement of B with respect to A. And this time, on your moment diagram, we are now going to involve a lever arm, x bar with respect to B. Okay? So referring to the elastic curve, we let tangential displacement of B with respect to A be the vertical distance from point B to the tangent of the elastic curve A. So T tangential displacement of B with respect to A is the vertical distance between point A and point B. Okay? So this distance is called the tangential deviation of B with respect to A. So to calculate the tangential deviation, we first determine the contribution or dt of the infinitesimal element PQ, and then use uh, tangential deviation of B with respect to A is equivalent to dt from point A to point B. Okay, so if we are to add the contributions of all elements between A and B, as shown in the figure, dt is the vertical distance at B and the tangent shown drawn to the elastic curve P and Q. Recalling that slopes are very small, we obtain the geometry dt is equivalent to x prime d theta. So TBA is equivalent to dt from A to B is equivalent to the integral of x prime d theta from A to B. Okay. Then, we substituting d theta, we obtain the tangential deviation of B with respect to A is equivalent to the integral of m over EI x prime dx from A to B. Okay? So, we can express this equation as the tangential deviation of B with respect to A is equivalent to the area of m over EI, which is the diagram, area of the diagram, evaluated from point A to point B, times the lever arm x bar with respect to B. So this is our two equations. So that is the second moment area theorem. So note that the first moment area represents the right-hand side of the equation is always taken about the point at which the tangential deviation is being computed. Okay, so do not confuse with TBA and TAB because these two are not equal. Okay, tangential deviation of A with respect to B, tangential deviation of B with respect to A. Okay, so signs and conventions. So following the rules of sign illustrated in figure 6.7, apply to the two moment area theorems. The tangential deviation of B with respect to A is positive if B lies above the tangent line. Okay, so this is my tangent line. B is above the tangent line, therefore it is positive. So, and negative if B lies below the tangent line. If this is the tangent line, B is below the tangent line, it is negative. So positive theta B with respect to A has a counterclockwise direction, whereas negative B over A has a clockwise direction. Theta B with respect to A is counterclockwise. Theta B with negative theta B with respect to A is clockwise in direction. So bending moment diagrams by part. So if we are going to solve our equation, it would be best if we use the bending moment by parts. Okay, so moment by parts, it would be a lot easier. So The application of moment area theorems is practically only if the area under the bending moment diagram and its first moment can be calculated without difficulty. So the key to simplifying the computation is to divide the bending moment diagram into simple geometric shapes: rectangles, triangles, and parabola. So we have these three geometric shapes that have known areas and centroidal coordinates. So sometimes the conventional bending moment diagram lends itself to such division, but often it is preferable to draw the bending moment diagram by parts. I repeat, preferable to draw the bending moment diagram by parts, which with each part of the diagram representing the effect of the load. Okay, so uh, for the procedure, okay, calculate the simple supported reaction and consider them to be applied loads. Okay, so we will be drawing the free body diagram after the computation of load and consider it to be a applied load. Introduce a fixed support at a convenient location depending on where you want it to be, as long as it is convenient for you. Okay, a simple support of the original beam is usually a good choice, but sometimes another point is more convenient. The beam is now cantilevered from this support. Draw a bending moment diagram for each load, including the support reactions of the original beam. If all the diagrams can be fitted in one single plot, do so, drawing the positive moments above the x-axis and the negative below the y-axis. Okay, so here we have a simply supported beam. Then what we did was to solve for the reaction, then place here a fixed support at C, then remove the other supports, then you have your support and place it as a applied load. So 200, and you have their shear C. Then draw here the moment of each of this loading. Okay. Then this is the moment diagram of each of this. This is the moment diagram of the whole structure if we are to combine these two areas. Okay. So the benefit of constructing the bending moment diagram by parts becomes evident when we compare the two figures. So here, okay. So here it's easier to locate the centroid. Okay, it's a lot easier to locate the centroid compared here. Okay. The former contains two simpler parts, a triangle and a parabola. Not only is the conventional diagram harder to divide into simple shapes, but also, before this can be done, the maximum bending moment and its location have to be found. Okay? So, this is the advantage of drawing the moment by parts. Mas madaling hanapin yung maximum moment of each part. Then you have the lever arm, wherein here you need to determine the maximum moment of the whole moment diagram, then divide it into parts, do the lever arm. Okay. As mentioned previously, the fixed support can be introduced at any location along the beam. Let us draw the bending moment diagram by parts for the beam by placing the fixed support at B. So here you place it here B. Okay. So as this location is not as convenient as placing it on point C, but it serves as an illustration. As a result, we have transformed the original beam into two cantilever beams by beams sharing the support at B. Applied forces consist of the both original reaction and distributed loading. Therefore, the bending moment diagram now contains three parts. So the summation of moment with respect to be on the right is equivalent to the summation of moment B with respect to the left. So they should be the same. But if you're going to check it here, it is more complicated than what we had on the first one. Okay? So when we construct bending moment diagram, this would help us determine the centroid. So we know that the centroid of a rectangle is at the center. For a triangle, it is 1/3 from the base or 2/3 from the top. If it is a parabola, it is 1/4 from the base or 3/4 from the top. And if it is a third-degree curve, then you have it here. Okay. Cantilever beams. So consider the deflection of the cantilever beam. So you have your deflection is equivalent to the tangential deviation of B with respect to A. Because the support at A is fixed, the tangent drawn to the elastic curve at A is horizontal. So from our previous video, I have told you that somehow the slope at the fixed support is 0 at a certain distance, then from there it will start to bend. Okay? Therefore, the tangential deviation of B with respect to A has the same magnitude as the displacement of B. In other words, the deformation of B is equivalent to tangential deviation of B with respect to A. And the tangential deviation of B with respect to A is simply the area of the M over EI diagram evaluated from A to B times the lever arm X bar with respect to VB. So likewise for a simply supported beam. Okay. So for our problems, we will discuss this on a paper to make it a lot easier.